So, in this talk, we will discuss Arzela-Ascoli theorem. So, before going to the main theorem, Arzela-Ascoli theorem, to prove that the compact subset of CXRN, a, a set is compact or is a subset of CXRN is compact if and only if it is closed, bounded and equicontinuous. So, this is the main Arzela-Ascoli theorem. So, before going to prove this Arzela-Ascoli theorem, let us prove the following Arzela-Ascoli theorem about the existence of convergent of subsequences. So, the theorem is here, which states that let X and D be a compact metric space and Fn be a sequence of functions from X to R, continuous functions, that is Fn be a sequence of real valued continuous functions defined on a compact metric space X, and this sequence is point-wise bounded and equicontinuous. Then the Fn is uniformly bounded and it contains a uniformly convergent subsequence. So, as we have seen that the point-wise boundedness does not imply uniform boundedness, but if the sequence Fn is point-wise bounded and equicontinuous, then, and of course it is defined on the set X is your compact, then Fn is uniformly bounded, and not only uniformly bounded, it contains a uniformly convergent subsequence. So, let us see the proof of this theorem. So, we first prove that the sequence Fn is uniformly bounded. Uniformly bounded, so by equicontinuity, because we are assuming that the sequence Fn is equicontinuous, that is to say the family of sequences, the family of functions from the compact metric space X to R is equicontinuous. So, by the equicontinuity there exists a delta is greater than 0 such that the distance between F and X, okay, and Fn, so you can say that the open ball with center at X lies in the open ball Fn inverse S1 Fn X, that is to say the open ball. So, this is the open ball with center at Fn X, radius 1, and of course this is your open set, and Fn is continuous function. So, this contains, so this is your open set. So, this open set lies in the inverse image of this. So, you can say that because Fn is greater than, there exists a, okay, remove all these things. Okay, please remove all these things. I start again. Remove all these things. I start again. Okay. Now I am starting now. Okay. Today we will discuss the Arzela-Ascoli theorem about the existence of convergent subsequences, and then later we will prove by using this theorem we will prove the main Arzela-Ascoli theorem. So now we state the Arzela-Ascoli theorem about the existence of convergent subsequence. Now here is let X be a compact metric space, Fn be a sequence of functions, okay, Fn in the CXR, that is Fn be a sequence of real valued continuous functions defined on a compact metric space X. And this sequence, or you can say this family of functions, is pointwise bounded and equicontinuous. Then this sequence is uniformly bounded and it contains a uniformly convergent subsequence. But as we have seen earlier, that a point-wise bounded sequence may not be uniformly bounded. But under the condition that the point-wise boundedness plus equicontinuity implies that Fn is uniformly bounded. Not only uniformly bounded, but also it contains a uniformly convergent subsequence. So, to prove this theorem, we first prove that the sequence Fn is uniformly bounded. Now, we are assuming that Fn is equicontinuous. So, by the definition of equicontinuity, there exists a delta is greater than 0 such that the open ball with center at x and radius epsilon lies in the F inverse x Fn inverse, the open ball with center at Fn x and radius 1 for all x in x and all natural number n. Okay, then now since it means what? It means that this is true for all x in x, and x, it means that if we consider for at each point x in x, capital X, we will have an open wall which will be a subset of this one. So in this way, the whole space X can be covered by such open balls. Okay, this is your open balls because this is your open balls. So inverse image of continuous inverse image of open set is open. So this is your open set. So this is means so X is compact. So there must be a finite set x1, x2, xk such that the X can be covered by a finite union of open balls with center at these points. So X is equal to this one. As X is pointwise bounded. So pointwise bounded means there exists the constant m1, m2, mk such that f and xj is less than or equal to mj for all j runs from 1 to k. This is by the definition of pointwise boundedness. Now we take M, capital M is equal to 1 plus maximum of 1 m1, m2, mk. Now for any given x, there is a j such that x lies in the open ball with center at xj and radius delta. It means what? It means now you can take and this is a subset of this one. Okay, and therefore X lies in this side. So X lies in this. Okay, and now you take it for all n. So if you take this, you take the Fn, you operate Fn both the side, then what we will get? We will get that F and X lies in F1 Fn X. It means that the mod of Fn X minus Fn Xj is less than 1 because the radius is 1, so it is less than 1 for all n. Now by reverse triangular inequality, so here we can use the reverse triangular inequality, we can write mod of Fn X is less than 1 plus Fn Xj. But Fn Xj is this is equal to this is Fn Xj, this less than or equal to Mj. So this 1 plus mj, but 1 plus mj is equal to m, so it is equal to m. So for all n, and now we are assuming we have assumed that x was our arbitrary, and so since x was arbitrary, Fn is uniformly bounded. So this we have proved that F is uniformly bounded. Now the second part is to prove that the Fn has a uniformly convergent subsequence. Okay, so to prove that Fn contains a convergent subsequence, okay, so we pick a countable dense set D of X. Then by the proposition 5.8.2 or previous proposal, we can find a sequence Fnj. Okay, so here you can see that this sequence, if X is your countable set, and Fn be a pointwise bounded sequence of functions Fn, then Fn has a pointwise convergent subsequence. So from here, because we are assuming that because X is your countable dense set. So X is countable. So by using this proposition, we can find a subsequence F and J that converges pointwise on D. For simplicity, we write F and J is equal to G, J. Okay. Note that the sequence Gn. So Gj is equal to F and J. So Gn is equicontinuous. Let epsilon be given. Epsilon is greater than 0 given. Then there exists a delta greater than 0 such that the open ball with center x and radius delta lies in Gn inverse. The open ball with center at Gn x and radius epsilon by 3. So this is again by the equicontinuity of Gn as we have taken here. So this is the continuity of Gn. Now since D is dense, it means that every x lies in as is an open ball with center at y and radius delta for some y is in D. So because this is dense, so every x must lie in some open ball with center at y and radius delta for some y is in D. Now again, because x is a compact, okay, so there exists a finite subset x1, x2, xk of D such that the whole x can be written as a union of such open balls as delta xj and j runs from 1 to k. As there are finitely many points and Gn converges pointwise on D, there exists a single n such that mod of Gn xj minus Gm xj is less than epsilon by 3 for all nm greater than 0 and all j runs from 1 to k. Let x be arbitrary, then there is some j such that x lies in the open ball with center at xj and radius delta, and so for all I natural number, the mod of gj x minus gj xj is less than epsilon by 3, and therefore for all nm greater than 0 we have the mod of gnx minus gnmx is less than or equal to this thing. This is by the triangulation. But this is less than epsilon by 2. This is epsilon by 3. This is less than epsilon by 3. This is less than epsilon by 3. So this term is less than epsilon. It means what? It means that Gn is a Cauchy subsequence, and because the Cauchy subsequence of real numbers and R is compact, and so it is a convergent, uniformly convergent, because here we are taking this is true for all n. So this the R is complete, so Cauchy sequence, and so it is uniformly convergent. Now as a corollary, we have that if X is a compact metric space and D is a subset of CXR. CXR means set of all continuous functions defined on a compact metric space X to R. Okay, so this set D is closed, bounded and equicontinuous, then D is compact. Okay, this we can prove by using the previous theorem. So here is the only thing is that we are taking X is compact and D is a subset of CXR. Basically what we want to prove that if D is a closed, bounded and equicontinuous subset of CXR, and then it is compact, and vice versa. So here is we take if D is a subset of CXR, is closed, bounded and equicontinuous, then D is compact. So this we get from the previous result. Now before proving the main result, main Arzela-Ascoli theorem, we prove the following proposition. The proposition says that let X dx be a compact metric space. So X is a metric space with metric X dx. Okay, Fn be a sequence of bounded and equicontinuous functions from the compact metric space X to Rn. then this sequence has a subsequence converging to Cx and Rn. Cx, Rn. Okay, that you can say that it is the has a convergent subsequence. So what you have, we basically here is we have if it is compact is a sequence pointwise bounded equicontinuous, then this sequence contains a uniformly convergent subsequence. So here is a Fn from Fn is the sequence of real valued continuous functions defined on the compact metric space X. Now we instead of R we are taking Rn. So here is we have this Fn be a bounded and equicontinuous sequence. Bounded means uniformly bounded, not pointwise bounded. So uniformly bounded and equicontinuous. Okay, then Fn has a subsequence converging in this space. So let's prove. So since X is compact, so by theorem 4.3.1, it is totally bounded, and then every totally bounded metric space is separable, so it is separable. So X is your separable. Therefore, X has a countable dense set A. Okay, let us take A contains the element A1, A2, An, and so on. And since Fn is bounded and A is countable, so by previous proposition, we can find a sequence Gk of Fn such that the sequence Gka converges for all A is in A. So this sequence converges. And now since Cxrn is complete, we have seen it suffices to prove that Gk is a Cauchy sequence. Okay, so every Cauchy sequence in a complete metric space is convergent. So we will prove that this sequence, basically it is a subsequence of the sequence Fn, is convergent. So that is for every given epsilon positive, we have to find a positive integer n such that this is holds good. So for this, now take since Fn is equicontinuous, then by the definition of the equicontinuous, there exists delta is greater than 0 such that the d Fn x Fn y, that is to say the distance between Fn x and Fn y is less than epsilon by 4 for all n, whenever the distance between x and y is less than delta. Now since Gk is a subsequence of Fn, we clearly have the distance between Gkx, Gky is less than epsilon by 4 for all k. Now choose a finite subset A delta of A such that any element in X is within less than delta of an element in A delta. Since the sequence AGKA for all A is in A delta, this sequence we have proved is converged. Since all the sequences for all A converge, they are all Cauchy sequence, and so we can find a positive integer n such that the distance between G and GMA is less than epsilon by 4 for all A in A lambda, whenever nm greater than or equal to. Here we are using that A lambda is finite. Okay, for any x we can find A in A lambda, A delta such that the distance between x and A is less than delta. But then for all nm is greater than n, we have the distance between G and x plus Gm and x is less than or equal to this thing. This we can use the triangular inequality. But this term is less than epsilon by 2, we have seen epsilon by 4, this is less than epsilon by 4, this is less than epsilon by 4. So the whole thing is less than 3 epsilon by 4. Now since the above inequality holds for all x in H, this is true for all x, we have the rho which we have defined, rho is equal to supremum of this one. So the rho of the distance between G and NMGM. So this is less than 3 epsilon by 4, and but this is less than epsilon, so this is less than. It means that GK is a Cauchy sequence in a complete metric space and thus converges. So this way we have proved that the Gn is a Cauchy sequence in a complete metric space and therefore it is a convergent subsequence. It remains to prove that the original sequence Fn really has a subsequence Gk such that Gka converges for all A is in N. We begin a little less ambiguity by showing that Fn has a subsequence Fn1 such that Fn1A1 converges. Okay, recall that A1 is the first element in our listing of countable set A. Now, we show that Fn1 has a subsequence Fn2 such that both Fn2A1, Fn2A2 converge. Okay, continue taking subsequences in this way for each natural number j. We find a subsequence Fnj such that Fnja converges for any A is equal to A1, A2, Aj. So finally, we construct the subsequence Gk by combining all the subsequences Fnj in a clever way. Now let us construct Fn1. Since the sequence Fn is bounded, Fna1 is a bounded sequence in Rn, and by Bolzano-Weierstrass theorem 4.2.1, it has a convergent subsequence Fnk A1, and let Fn1 consist of the functions appearing in this subsequence. If we now apply Fn1 to A1, A2, we get a new bounded sequence Fn1, A2 in Rn with a convergent subsequence. We let Fn2 be the functions appearing in this subsequence. Note that Fn2A1 still converges as Fn2 is a subsequence of Fn1. Continue in this way, we see that for each natural number j, we have a subsequence Fnj such that Fnja converges for all A runs or for all A is equal to A1, A2, Aj. In addition, each sequence Fnj is a subsequence of the previous sequence. Okay, we are now ready to construct a sequence Gk such that Gka converges for all A in capital A. We do it by a diagonal arrangement, putting A1 equal to the first element in the first sequence Fn1, G2 equal to the second element in the second sequence Fn2, etc. In general, the kth term in the G sequence equals the kth terms in the kth F sequence Fnk, that is Gak is equal to Fnk. Note that except for the first few elements, Gk is a subsequence of any sequence Fnj. This means that Gka converges for all A is in A, and the proof is complete. Similarly, as we have seen in the previous we have a corollary, and which is a very simple corollary, and it can be derived very easily from the previous proposition. We say that if X is your compact metric space, then any closed, bounded and equicontinuous subset K of CXRN is compact. So, if X is compact, then any closed, bounded and equicontinuous set capital K in CXRN is compact. So, in view of proposition 5.8.4, any sequence in K has a convergent subsequence. And now since K is closed, the limit point must be in Q and hence it is compact. So this can be proved very easily by using the previous proposition. Now we are ready to prove the main Arzela-Ascoli theorem. So main Arzela-Ascoli theorem says that if X is a compact metric space, okay, X is a compact metric space, CXRN is the space of all continuous functions defined on the set X to Rn. So let K be a subset of this set. So the set K is compact if and only if it is closed, bounded and equicontinuous. So any subset of CXRN where X is your compact is compact if and only if it is closed, bounded and equicontinuous. So in view of this, if it is closed, bounded, equicontinuous, then it is compact. So one way is obvious. Okay. So in view of above corollary, it remains to show that the compact set K is closed, bounded and equicontinuous. Okay. So since K is compact, it is closed and bounded. So we only left to prove that it is equicontinuous. Okay. So to prove that K is equicontinuous, assume that K is not equicontinuous. Then there exists an epsilon greater than 0 such that for any delta is greater than 0, there is a function f in K and points x1, x2 in X such that the distance between X and Y is less than delta, but the distance between f of X and f of Y is greater than or equal to epsilon, where the distance is taken in Rn. Okay. Now since K is compact, okay, there is a subsequence Fnk of Fk which converges uniformly to a point F. Okay. Also since X is compact, the corresponding subsequence Fnk of Xn has a subsequence Xnkj converging to a point A in capital X. And now since the distance between X and Kj, Y and Kj is less than 1 over Nkj, the corresponding sequence Y and Kj of Y's also converges to A. Now since Fnkj converges to F and X and Kj, Y and Kj both converge to A, by exercise 5.6.1 we have that this sequence converges to F of A and this sequence can also converges to F of A. But this is not possible, as we have seen that the distance between F X and Kj and distance between and F Y and Kj is greater than epsilon from here. So we can take here this is greater than epsilon. So but this is not possible. So we reach to a contradiction, and therefore our assumption that K is not equicontinuous is not correct. So this way we have proved the Arzela-Ascoli theorem. We say that if X is compact, then a subset K of CXRN is compact if and only if it is closed, bounded and equicontinuous. As I am mentioning all the time that I am putting several exercises, okay, and these exercises basically are based on the results which we have already proved, okay, or we have already discussed. So the first exercise says that let Fn be a sequence of functions Fn, a sequence of functions, real valued sequence of functions defined on the closed interval -1 to 1, defined as Fnx is equal to nx divided by 1 plus n square s square. Okay, prove that Fn is uniformly bounded, converges pointwise to 0, but there is no subsequence that converges uniformly. So how we can prove this one? So this we can prove that we will have to check whether there is any condition of Arzela-Ascoli theorem which is not satisfied. So if you can prove this one, you will get the answer. So the next result, next exercise is also the similar one with the previous exercise, but only the here is we have changed the function f n x is equal to 1 over x minus n square plus 1. So again, you have to check whether which hypothesis of Arzela-Ascoli theorem is not satisfied, and then you will get the answer. Now, Fn, if Fn is an equicontinuous family of functions Fn from the closed interval 0, 1 to R, and Gn is a function from the closed interval 0, 1 to R is continuous, then prove that Fn plus G is equicontinuous. So, this is the family of equicontinuous functions, and you add any continuous function in this one, then that family will also be equicontinuous. Okay, this is very simple, you can try. Okay, now we have proved that another exercise which says that prove that a compact subset K of C01R is nowhere dense set. Okay, now here is the important thing is that C0, look here is the very important thing. You can see that we have proved that if X is your compact set, so if X is equal to close 0, 1, so this is your compact set. Okay, so A is a compact set. So, and K is this any set, any compact subset of this set must be what? Must be so this is your okay. So this is your closed and bounded. Okay, so this is here. This is your compact set, and then you will have to prove that this set compact set K is nowhere dense set. Now, since every compact set is closed, in view of exercise 3.3.3, it suffices to show that each sphere with center at F and radius epsilon contains elements that are not in K. So, why Arzela-Ascoli theorem? Compact sets are equicontinuous, and hence we need only to prove that the open ball with center at F and radius epsilon contains a family of functions that is not equicontinuous. So, for that we define for each natural number we define Gn, a function Gn in this way, and then Gn is not equicontinuous and F plus G is in the open ball with center at F and radius epsilon. But since F plus Gn is not equicontinuous, okay, as we have proved in this previous theorem, here is we have the previous theorem, all these functions cannot be in K, and hence the open ball with center at F and radius epsilon contains elements that are not in K. Okay, so there are several others. So prove that the space C01R is not a countable union of compact set. Okay, since this C closed interval 01R is complete by bare category theorem, it cannot be countable union of nowhere dense set, and then by this exercise we obtained the desired result. So somewhere you have seen that you need to prove, you need to use some kind of the result which we have already done in the previous lectures, or just on the same lecture. So just you try to utilize the results which we have already proved in just in few lines, so you can get the answer of all the exercises which I have mentioned over there. Okay, so this is the end of the chapter which is on equicontinuity. You can say that. Okay, so I stop over here. Thank you very much.